Great. So for our first research talk of this summer school, we're very pleased to have Allison Miller. The title of her talk is Embedding Spheres in Simple Four Manifolds.
Thank you. And I'm very delighted to be here and have the opportunity to tell you all about this. And I wanted to start by saying, normally I promise that I will try and look at the chat if I can. In this setup, I can promise that I will not see the chat. So please feel free to unmute and ask questions if you have them, or if you put them in the chat, maybe an organizer will be kind and ask it out loud, but I won't see it. Okay. So I want to start by reminding you of something that appeared in at least one, if not more, of the mini courses, which is this simple four manifold that we can associate to any knot in S3 and any integer n. And I'm going to call it the n trace of the knot. And what we do is we take the four ball with boundary S3, we find our knot sitting in the boundary, and we attach a two handle, a thickened disk, to before along that knot with framing n. And so the sort of curvy calculus picture of it is not quite that simple. You take any diagram you choose of your knot K and attach an n-frame two handle. And the notation I'm going to use for this over and over again is x sub n of k. Okay. So some key facts that I just want to reiterate or tell you if you've never seen them before, which is, first of all, what's the boundary of the n trace on k? It's the Dane surgery on k with the same coefficient. The next thing is that you can see that the n trace is homotopy equivalent to S2, no matter what n is. And you can sort of imagine seeing the cone on the knot sitting in before and the core of the two handle sitting in the two handle. That's really the S2 that it's homotopy equivalent to. And then finally, that's sort of ambiguous looking thing. Let me make it very homotopy looking and not homeomorphic looking. The last thing is, okay, what if we take the unknot? What do we get? Well, it turns out we get a disk bundle over S2. And in fact, sort of we can pin it down, it's the Euler number n. Disk bundle over S2. And one way to think about that is that for any of these, because it's homotopy equivalent to S2, the second homology is just the integers, fine. But we have this intersection form. And the intersection form on this sort of generator you expect is just n. So those are some key facts about knot traces. Why should we care? Well, there are, I think, a lot of reasons. One of them is that they're early and good examples of exotic four manifolds. Also, I think I can just say, go see Lisa's mini course for many more reasons why you might like traces. And secondly is from a perspective of if you care about sliceness or not concordance, these are sort of natural to think of as a weakening of sliceness at some point in some way. And so what do I mean by that? I mean that if K is slice, well, that implies that there exists an embedded two-sphere in the n trace, and this is for any n and n, that generates, I'll say, second homology. If you prefer, we can do pi2 since this is a simply connected four manifold. And it's worth sort of, advertising as a notable open question that the converse in the n equals 0 case is really hard. The converse, proving that the converse is false in the n not equal to 0 case is not so hard and has been done for a long time, I will say. So are there any questions before I move on to talk a little bit more about our result? Okay. So first of all, some language. When this sort of right-hand side is true, we sometimes say that K is n-shake slice. Clearly from the definition, it's really a property of the trace of the knot. And I think I was inspired by the mini courses that had exercises included. And so I have also included an exercise that gives some intuition as to why you might call this n-shaped slice, because I think from the 4-dimensional perspective, it's very unclear. So the fact is that K is n-shaped slice is defined above if and only if for some K greater than or equal to 0, the link, the 2K plus 1 component link that I'm calling here K and K. And so this box up here denotes that all of the strands are tied into the knot K. This box here indicates full twists. And I want to draw your attention to the fact that the orientations are alternating. Okay, so for some K greater than or equal to 0, the link KNK bounds a planar surface in B4. And so you might call this link on the right is sometimes called a shaking, an end shaking of K. You sort of shook it about and taken a lot of parallel copies. So far I haven't said anything about category. And that's because so far everything I've said, the definitions make sense in the smooth setting, the definitions make sense in the topologically locally flat setting, and sort of just take your pick. But the result I want to talk about today, which is joint work with Peter Feller, Matthias Nagel, Patrick Orson, Mark Powell, and Aru Ray. This is really in the topological category and certainly very, very false in the smooth category. And so what it is it's going to give some algebraic, very computable criteria that together imply that a knot is topologically n-shaped slice. So I will in a second comment on why we're restricting to n not equal to 0 here, and then tell you some more about the conditions. But first, what are the conditions? First of all, the first one is that the ARF invariant of the knot should vanish. And so if you don't know, the ARF invariant is a Z mod 2Z valued invariant of a knot. You can compute it from the Alexander polynomial very easily. It's an invariant of the double branch cover of the knot even. It's nice. The second condition is in terms of the Tristram-Levine signatures of the knot, and it says that some of those also vanish. So for which ones? This is where n starts to come into it. Well, for all omega in the unit circle, complex numbers, with omega to the n equals 1. So the nth root of unity signatures vanish. And finally, if we look at the absolute value of n branched cover of K, okay, that's the 3 manifold, we can look at its first homology. And the condition here is that this is trivial. So you can really, for any given knot that you care about and any n, you can compute these things. And you can just sort of say, okay, well, check, 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 these all vanish. I'll give a nice corollary in a second that sort of shows you how flexible this can be. Then my knot has to be topologically n-shaped slice. So maybe I'll comment on, let me zoom out here so you can still see the statement. What's happening with n equals 0? Well, there isn't really a 0th branched cover. I could have restated this in a way that was general, that worked for any n and n. It's just a little bit harder if you haven't seen sort of different kinds of weird homology. But our result for n equals 0 would just be that if you have trivial Alexander polynomial, then your 0 shake slice, which we knew already, because if you have trivial Alexander polynomial, then by famous work of Friedman, your slice topologically, and so you're certainly 0 shake slice. And so where do these conditions come from? Might be a natural question. So condition A, and I'm going to say most of condition B, are actually requirements for being n-shake slice. Okay, what do I mean by most of B? This is going to be addressed mostly at people who know concordance obstructions reasonably well, which is that not all Tristram-Levine signatures are sliceness obstructions. So there are slice knots that don't have a completely zero Tristram-Levine signature function. So the obstructions to or requirements for being n-shake slice are basically item B, but restrict to those that are actually requirements for being slice. So in particular, look at the prime power roots of unity, prime power order dividing n. Great. But the rest of B, and certainly all of C, is not at all even a requirement for being slice. But you can, and I think should, think of these as being weakenings of Alexander polynomial equals 1. In particular, well, there's a formula for the order of the first homology of a cyclic cover of the knot that's just in terms of the Alexander polynomial. And it is also true that if you have trivial Alexander polynomial, then all of the Levine-Tristram signatures vanish. So for now, I'll just sort of say that hand-washy slogan of they're weakenings of trivial Alexander polynomial. So this is a good time for me to pause and ask if there are questions at this point.
Can you scroll back up to the picture for shake slice for a second?
Yeah. That one?
Yeah.
Yeah. There's going to be another picture actually coming quite soon that explains where this picture comes. It's a hint for the exercise as well as being useful for us.
Okay, great.
That might make you happier about where that came from.
Thanks.
And can I ask a small question quickly? Do you know,
Yeah.
you mentioned a knot that is slice but has Tristram-Levine signatures that are non-zero for some omega. Is there like a knot in the knot tables that's like sort of the smallest known one that has this property?
Yes, probably. I don't know it off the top of my head. I think there are some pretty small ones that at a sixth root of unity have non-trivial signature function. And I'm pretty sure, I don't think he was the first, but I think Chuck Livingston has some work sort of showing all of the non-triviality you can get as well.
And those non-trivial omega, those are presumably near the roots of the Alexander polynomial?
Yes, even, yes.
At the root,
yes. So,
yes, okay, great.
Yes.
Thank you.
Yes, yeah, good question. Any others?
So I had a quick question.
Mm-hmm.
So the Tristram-Levine signatures, the conditions on them, are they relating to the sliceness of the knot or shake sliceness? The ones you say are requirements for being n-shake slice?
So yeah, that's a great question. So maybe I'll just say here, here's the fact. If K is n-shake slice, then arf K equals 0. And let me just write it. Okay, so the Tristram-Levine signature is 0 for omega with omega to the n equals 1. And I'm going to write the order of omega for, as a element in a multiplicative group, I guess, is a prime power. And so those are requirements, obstructions to being n-shake slice. There are also certainly obstructions to being slice, except for slice, you don't even have to worry about the omega to the n equals 1 thing. You get something much stronger.
Thanks.
Yes. Anything else? Okay. So I promised. Oh, okay. Before we do the proof idea, which will include the fun picture, I promise, there's a nice corollary of this. So pick any knot with arf invariant 0. This is, in a reasonably precise sense, half of all knots. So you could take a large connected sum of trefoils as long as it's even. You can get very, very non-slice knots in this fashion. And then take the N1 cable of it. Again, this possibly always, but certainly often preserves non-sliceness. But it's topologically n-shake slice. And this is super not true in the smooth category, as you can use D invariance, and I'm happy to say things about that at the end, but there are smooth things that tell you that there's no way that this is true there. Okay, so what's the proof idea? Pretty roughly. So sort of inspired by and following Friedman, we're actually going to prove an if and only if statement rather than the if statement. And sort of the proof of the only if gives us ideas about how to prove the if. So what's the theorem of Friedman that we're sort of spiritually mimicking here? Well, it's exactly the one I referred to earlier, that if you have a knot, given any knot k, the Alexander polynomial of k is trivial if and only if there exists a disk in B4, boundary of disk is k, and here in the future, everything I talk about is locally flat. So I'm probably going to stop saying that. There exists D2 embedded in B4, boundary of k, so topologically slice, but the thing that makes it an if and only if is that such that the fundamental group is as simple as it can be. Another good exercise is to show that for any slice disk, the first homology of the complement is the integers. So that's also the simplest possible fundamental group. And that's the if and only if statement that Friedman gets. Okay. So what's the if and only if statement that we get? Let me mostly copy it from here. It's really somehow rather similar. Come on. Though longer. Okay, so for k and S3 and n not equal to 0, we have these three conditions. And we say that these three conditions are true if and only if, well, k is topologically n-shake slice. Okay, that means that there's a sphere embedding in the n trace, generating second homology. So via this sphere S2, and such that the fundamental group of the complement is as simple as possible, is the same as first homology of the complement. And again, if you want more exercises, you can prove that the first homology of the complement of such a sphere is always Z mod NZ. You can tell that my collaborators are sort of split between pronouncing it Z and Z because I come out with things like Z mod NZ to say. Okay, great. So this is the if and only if statement. And so now what I would like to spend the rest of my time doing is just telling you a little bit about the ideas behind the proof. And so I actually promised a picture. This is the picture I promised to City. So first I want to tell you, this is a schematic picture of what happens when a knot is n-shake slice. And I should say that looking at the intersection of this sphere with the S3 is where you get that shaking picture, that intersection. And maybe something worth pointing out is that this really does rely in the topological category on the topological transversality results that Aru is going to start telling us about soon. So there's some hard stuff lurking in the background of even this direction, which is somehow the easier direction. So what's the outline here? So if we have a generator for second homology, we have S and K generating H2, then what we're going to look at is W, which I'm just going to call the exterior of S. Okay, so what do we know about W? It has like two or three key properties here. The first one is, well, it's a cobordism. It has two boundary components. And what are they? We can think about it sort of as the outer boundary, which is just the boundary of the trace, i.e. the end surgery, and then the inner boundary. And the inner boundary maybe takes a little bit of more thought, but it ends up being the lens space, LN1, or maybe it's more natural to think about it as the end surgery on the unknot. The second thing is that this is not just any cobordism. This is an integer homology cobordism. And so what that means, just to remind you, is that if you include either boundary component into the four manifold, that gives you isomorphisms on homology. That takes a little bit of more thinking, and maybe some long exact sequences. And the final thing, which is straight from, is straight from this, but I'll write it down anyway, is that the fundamental group of W is very simple. And whenever you have a W like this, you can draw some conclusions that give you the vanishing. Though I should say here and repeat that there are other proofs, certainly for the ARF invariant and for some of the Tristram-Levine signatures vanishing due to Robert Patello and Tristram. So that's sort of supposed to be the easy direction, though. But the reason I really wanted to talk to you about it is because, in a certain sense, this direction gives us the idea of how to do the other direction. And the idea is build W. And then actually all of the end trace. So I've broken this down into three sort of broad steps, and I'm going to be kind of vague at various points about what goes into them, but please feel free to ask. So step one is just to get any cobordism between the end surgery on K and the end surgery on the unknot. Okay, there's an asterisk there, because that's a little bit of a lie. There are some technical things you want. There's some work that goes into this, but it's not that bad. Okay, and then I should say, this is sort of, also we saw this in one of Aru's lectures. You can make the pi 1 be what you want to by doing surgery along curves in this four manifold. So I'll put that in that step. Okay, but I want to emphasize, you can make pi 1 be right, but it's really not going to be a homology cobordism. You have no reason to believe at this point that it's a homology cobordism, just that the fundamental group is what you want it to be. Okay. So step 2 is make it a homology cobordism. And this is sort of one of the pieces where there's a big machine lurking in the background. And so I want to say a little bit about what's going on here. And really what I want to say is that the key tool is something called surgery theory. Surgery gets used in too many ways. But what is really going on here is that there are obstructions to having, I'll even emphasize here, algebraic obstructions to having a homology cobordism between S3 and K and S3 and U with this nice fundamental group. And surgery theory, sort of in dimension 4 here, tells us that if these algebraic extractions equal 0, if they vanish, then you can actually change your thing to an integer homology cobordism. And a key part of that, or a key feature in why this works, is that we're in this setting with a very simple, nice fundamental group. And so I know Aru alluded to this, which is, I think so far most of the results we've seen have been simply connected, but in particular, this work of Friedman requires the fundamental group to be something that's called good, which is a horrible and technical definition, that possibly all groups are good, but certainly abelian groups are definitely good. And in fact, we know wider classes of good groups. And so that's a key sort of step in the process here. That's why we get these conditions specifically for Z bar NZ. Okay, so now we've built the homology cobordism. So we're really almost there. And so what we're going to do is we're going to build something new. I'm going to call this Z, I guess. What we're going to do is we're going to take Z, and remember it has two boundary components, one of which is N surgery on the unknot. And we're going to stick on the N trace of the unknot. So why are we doing this? Well, we're doing this because the N trace of the unknot certainly has a nice embedded two-sphere generating second homology. And so if we can recognize X as being homeomorphic to the N trace, then we're done. We've won. We've found a topologically embedded two-sphere sitting inside our N trace. And so the key tool here, well, I will say, we've heard about the classification of smooth four manifolds, smooth simply connected four manifolds by their intersection form. That actually generalizes to a smooth closed four manifolds. That actually generalizes to topological closed four manifolds by their intersection form, with the addition of sort of another piece of information, which is something called the Kirby-Zieberman invariant. And then that's been generalized even further, and the work we rely on is due to Boyer, which tells us how to understand when simply connected compact four manifolds are homeomorphic. And okay, so first of all, you need their boundaries to be homeomorphic, but we have the right boundary. And it basically boils down to the intersection form, and we can check that that's right, along with this mysterious Kirby-Zieberman invariant. And this is another place where the ARF invariant sort of shows up. And I think I will stop there for now. Thank you very much for your attention.
Thank Allison for a wonderful talk.